Hello, this is Dr. Claire, and we're going to run through an example about how to tell if a population is actually in Hardy Weinburg equilibrium. All right. So here's our little population. We have 1,000 kangaroos. In order to tell if this population of 1,000 kangaroos is in Hardy Weinburg equilibrium, we need to figure out what the observed genotype frequencies are. And then we need to compare those observed genotype frequencies to the genotype frequencies that we would expect from Hardy Weinburg equilibrium. All right. So those are the two things that we're going to be doing. So if you look at our population here, we have kangaroos that look different. We've got kangaroos with long tails, kangaroos with medium tails, kangaroos with short tails. Okay, and this is determined by a single gene, A, and that gene has two alleles. So you can be a big A homozygote, in which case you have a long tail. You can be a big A, little a heterozygote, in which case you have a medium tail, or you can be a little a homozygote, in which case you have a short tail. Okay, so if we look at our population, the first thing we want to do is we want to calculate our observed frequencies of these different genotypes within the population. So observed genotype frequencies. That basically means we look at the population, we observe how many there are of each of these things, and then we calculate the frequency. Okay? So in this case, if there are 90 long-tailed kangaroos out of 1,000 kangaroos total, you simply take 90, you divide it by 1,000, right? Same thing goes for the heterozygotes. There's 420 of them, divide that by 1,000. Same thing for the homozygotes, 490 of them, divide that by 1,000. So here are our observed genotype frequencies. This is what we actually see in the population. Now, in order to tell if this population is in Hardy Weinburg equilibrium, we need to compare these observed values to what we would predict based on Hardy Weinburg theory. All right? So hopefully you remember from the last lecture that the formula that we have for Hardy Weinburg is p squared plus 2pq plus q squared equals 1, right? So that's our Hardy Weinburg formula, but we need to get that p squared, 2pq, q squared, right? So we have to calculate p and q. Now p and q are the allele frequencies in the population, the observed allele frequencies, all right? So if we look at our individuals here, each individual has two alleles, all right? So let's start with the big A allele. What individuals in this population have big A alleles? Well, the long-tailed kangaroos have big A alleles. Each individual who's long-tailed has two big A alleles, right? But there's another kind of individual that also has big A alleles, and those are the medium tails. They're heterozygous, so each medium tail kangaroo has one big A allele. Okay, so what you want to do is you want to count up, literally count up the number of big A alleles that you have. So for each homozygote, you have two. So you do 2 times 90, right? Plus 1 times the number of heterozygotes, because there's only one big A allele in each heterozygote. So 1 times 420 over the total number of alleles in the population. All right, now we have 1,000 individuals. How many alleles does each individual have? Each individual has 2 alleles because they're diploid. So you want to divide that first number that we said by the total number of alleles. So we have 1,000 kangaroos, each one has 2 alleles, so it's 1,000 times 2. So what that looks like is this. So 2 times the number of homozygotes plus 1 times the number of heterozygotes over the total number of individuals times 2. So that gives us an allele frequency of the big A allele of 0.3. Okay? Now you can do the exact same thing for the little a allele. So 2 times the number of homozygotes plus 1 times the number of heterozygotes over the total number of alleles. Or you can take a little bit of a shortcut, because p plus q always equals 1. So you can just subtract p from 1, and that'll give you q. Okay, so that's a little bit of a shortcut. You do it both ways. Prove to yourself that you get the same answer both ways. But as long as you're doing your math right, that should always work. If you're not confident you're doing your math right, it's probably good to do it the long way, because then you can check yourself and make sure that when you add them together it equals 1, and that's one way to check your math, okay? So now we have observed allele frequencies of P and Q. So P is 0.3, Q is 0.7, okay? So now that we have P and Q, we can plug those in to calculate our expected Hardy Weinburg genotype frequencies. Okay, so hopefully, cast your mind back to that previous lecture. How do we calculate the expected genotype frequency in Hardy Weinberg equilibrium for a big A individual? Well, that's going to be P times P squared, right? And for a little a, it's going to be Q squared, right? Because it's the probability that you get a big A from your, a little a from your mom times the probability you get a little a from your dad. So it's Q times Q squared, right? Okay, hopefully good. And then 2PQ is your heterozygote. We just went through this in the last one, so hopefully this all sounds familiar. So that's going to look like this, all right? P squared, 2PQ, and Q squared, right? You take your allele frequencies over here, you plug them in, and you get 0.09, 0.42, and 0.49. Now you have observed allele genotype frequencies, and you have predicted genotype frequencies, and you want to compare them. So we're comparing the observed and the predicted. There they are. They're the same. When your observed genotype frequencies are the same as your predicted genotype frequencies, the population is in Hardy Weinberg equilibrium. If your observed genotype frequencies are different than your predicted genotype frequencies, the population is not in Hardy Weinberg equilibrium. One really, really common mistake that a lot of people make is they look to see if P squared plus 2PQ plus Q squared equals 1, and they're like, it equals 1, we're in Hardy Weinberg equilibrium. No, that just means you did your math right. P squared plus 2PQ plus Q squared will always equal 1. If it doesn't equal 1, you've done your math wrong somewhere. Okay, so that has nothing to do with whether you're in Hardy Weinberg equilibrium or not. It only has to do with whether you did your math right. The important thing is that your observed genotype frequencies are either the same or different from your predicted genotype frequencies. Okay? Okay, and so if you're different, then something interesting is going on, and we'll talk about that more for Friday. Okay, have a good day.